Going. Looks like it's working. All right. So today we are going to finish up section 10.3, which looked at the Taylor and Maclaurin series. Okay, so let's say, for example, if we wanted to find the Taylor polynomial, p sub 3 of x for f of x is equal to 5x to the 1/4 power at x is equal to 5. Okay. Now your p sub 3 of x, that just means you're going up to the term with the third derivative. So you're going to f of c plus f prime of c times x minus c plus the second derivative at c divided by 2 factorial times x minus c squared plus the third derivative at c times 3 divided by 3 factorial times x minus c to the third power. Okay, well, we know that f of x is 5x to the 1/4 power. And our f prime of x, we bring down the 1/4, that's 5 over 4, times x to the 1/4 power minus 1. So 1 over 4 minus 3, or minus 4 over 4 is negative 3 over 4. Or you can rewrite that as 5 over 4 times x to the 3/4 power. Now our second derivative is we bring down the negative 3/4 and multiply that by 5 over 4. So that gives us negative 15 over 16 times x to the power of negative 3 over 4 minus 1. So negative 3 over 4 minus 4 over 4 is negative 7 over 4. Where you can rewrite that as negative 15 and make that 5 a little neater, divided by 16 times x to the 7/4 power. And bring that 7 down a little. Here we go. And our third derivative, we bring down the negative 7 over 4. That gives us 105 over 64 times x to the power of negative 7 over 4 minus 1 is negative 11 over 4. Or you can rewrite it as 105 divided by 64 times x to the 11/4 power. Now at x equals 5, that means our f of 5 is just 5 times 5 to the 1/4 power. Or you could just say 5 to the first power times 5 to the 1/4 power is 5 to the 1 plus 1/4 power. Or 5 to the 5/4 power. And just let me kind of separate these a little bit. Okay, so the first derivative at x is equal to 5. So that's 5 divided by 4 times 5 to the 3/4 power. So if we wanted to, we could simplify this a little bit more by factoring out that 1/4. And rewriting this as 5 to the first power divided by 5 to the 3/4 power. Okay, and we can simplify that even more because we know that x to the power of m divided by x to the power of n is x to the power of m minus n. So 5 to the first power divided by 5 to the 3/4 power is 5 to the 1 minus 3/4 power. So 4/4 minus 3/4 is just 1/4. So this simplifies to 5 to the 1/4 power divided by 4. Okay, now if we look at the second derivative at x is equal to 5, we know that's negative, I should use this form, negative 15 divided by 16 times 5 to the 7/4 power. And just to simplify this a little bit more, that negative 15, we'll say negative 3 times 5, or 5 to the first power, whichever one, divided by 16 times 5 to the 7/4 power. Okay, so that's equal to negative 3 over 16, 5 to the first power, divided by 5 to the 7/4 power, is 5 to the 1 minus 7/4, which is negative 3/4. So we can write that as negative 3 divided by 16 times 5 3/4. Or if you wanted to, you could rewrite it depending on which form you want it in. Negative 3 divided by 16 times 5 to the 3/4 power. You can multiply that by 5 to the 1/4 power divided by 5 to the 1/4 power. If you multiply those two, you just get 5. That's negative 3 times 5 to the 1/4 power divided by 16 times 5, which is 80. So either one of those forms work, depending on which one you want. And for the third derivative, hopefully I have enough room. I should be able to get everything in that little bit of space. For the third derivative at 5, we have 105 divided by 64 times x to the 11/4 power. Zoom in a little bit. Oh, put the mouse out of the way. Here we go. So that gives us 105. We can actually expand that to 21 times 5. So we have 21 times 5. Oh, did I forget my 5? Nope, I didn't. Got to plug in my 5. So it should be 5 to the 11/4 power. So that's 64 times 5 to the 11/4 power. So at 5, we could just make that 5 to the first power. So we could rewrite this as 21 over 64 times 5 to the first power divided by 5 to the 11/4 power. 5 to the first power, 11/4 power, which is 5 to the 1 minus 11/4 power, which gives us negative 7/4. So we could rewrite that as 21 divided by 64 times 5 to the 7/4 power. Or, like we did here, if we want to have that 5 1/4 in our denominator like the previous two, we could just take that 21 divided by 64 times 5 to the 7/4 power and multiply it by 5 to the 1/4 power divided by 5 to the 1/4 power. And let me kind of separate these two to avoid confusion. Okay, so that gives us 21 times 5 to the 1/4 power divided by 64, and 5 to the 7/4 plus 1/4 power will give us 8/4, which is 5 squared. That gives us 21 times 5 to the 1/4 power divided by 1600. And we'll finish it up on the next page. All right. So that means our p sub 3 of x is equal to f of 5 plus f prime of 5 times x minus 5 plus the second derivative at 5 divided by 2 factorial times x minus 5 squared plus the third derivative at 5 divided by 3 factorial times x minus 5 to the third power. Excuse me. Okay, so that means it's equal to your f of 5, which is 5 to the 5/4 power, plus your f prime of 5, which is f prime of 5, looking at the wrong one, 5 1/4 divided by 4, well, 5 to the 1/4 power divided by 4, which is your f prime of 5, times x minus 5. Plus your second derivative at 5, which is -3 times 5 to the 1/4 power divided by 80 times 1 over 2 factorial, or you could divide that whole thing by 2 factorial, but I'll just multiply it by 1/2 times x minus 5 squared plus your third derivative, which is 21 times 5 to the 1/4 power divided by 1600 divided by 3 factorial. So I'll just multiply by 1 over 3 factorial, which is just 1/6, times x minus 5 to the third power. I swear. I always start off with too much room and end up squeezing it in there at the end. X minus 5 to the third power. Okay, so if we simplify it just by multiplying our denominators, we have 5 to the 5/4 power plus 5 to the 1/4 power divided by 4 times x minus 5 plus we have -3, or you can just make that -3 just to simplify it a little bit. 3 times 5 to the 1/4 power. Make that 5 a little bit bigger. divided by 80 times 20, which is 160, times x minus 5 squared, plus 21 times 5 to the 1/4 power, divided by 1600 times 6, which is 9,600, times x minus 5 to the 3rd power. Okay. Actually, this can be simplified one more time, only because 21, we know that's 7 times 3. And 9,600, that's 3,200 times 3. So the 3's cancel each other out. So our final answer is 5 to the 5/4 power plus 5 to the 1/4 power divided by 4 times x minus 5 minus 3 times 5 to the 1/4 power divided by 160 times x minus 5 squared plus 7 times 5 to the 1/4 power divided by 3,200 times x minus 5 to the 3rd power. And if you wanted to, you could factor out a 5 to the 1/4 power from each term, but that's not necessary. You can do it if you feel like having a little extra fun. All right. Any questions on that one? All right. Anyone? Looks like everyone's done. Okay, so let's say, for example, if we wanted to find the Maclaurin series or Maclaurin polynomial. P sub 1 of x for f of x is equal to 1 divided by 4x plus 8. Okay. So if you remember for the Maclaurin series, you know that c is equal to 0. And we know that our p sub 1 of x is just equal to f of c plus f prime of c times x minus c. So we're only going to the first derivative term. Okay. So we need to find, well, we already know f of x. We need to find f prime of x before we can plug in c is equal to 0. So our f of x, we can rewrite that as 4x plus 8 to the negative 1 power. Which means that our derivative, using the chain rules, we bring down the negative 1. So negative 1, or you can just put negative. Yeah, 1 is kind of unnecessary. Negative will work. 4x plus 8 to the power of -1 minus 1 times the derivative of what's inside, which is 4. So that gives us -4 times 4x plus 8 to the -2 power that we can rewrite as just -4 divided by 4x plus 8 squared. Okay, so we know that for the Maclaurin series, our p sub 1 of x is equal to f of 0 plus f prime of 0 times x minus c. Well, these are pretty cut and dry, so we can just do these right on the side. So f of 0 is just 1 over 4 times 0 plus 8, which is 1 over 8. And f prime of 0, we know that's -4 divided by 4 times 0 plus 8 squared. Where that 4 times 0 is 0, so we can just cross that right on out. So that's just -4 divided by 8 squared, which is -4 divided by 64, which we can still simplify to -1 over 16. So that means our p sub 1 of x is equal to f of 0, which is 1/8, plus f prime of 0, which is -1/16. Now you could have wrote minus, but I'll write negative first. Times x minus 0, which is just x. Nope, actually I should put in a 0 there. There we go. Or you can just make that negative, where our p sub 1 of x is equal to 1/8 minus 1/16 times x. All right, any questions on that one? All right. Oh, sorry. All right. Let's say, for example, if we wanted to find the first 4 non-zero terms of the Maclaurin series, for f of x is equal to sine of x. Excuse me. Okay, so we know that for our sine of x, our first four terms would be f of 0 plus f prime of 0 times x minus 0, which is just x, plus the second derivative at 0 divided by 2 factorial times x minus 0 squared is just x squared, plus the third derivative at 0 divided by 3 factorial times x minus 0 to the third power, which is just x to the third power. Okay, well, we know that. I'm just going to calculate this all in this box. So f of 0 is sine of 0, which is 0. Okay, we know f prime of x, or the derivative of sine, is cosine, which means that f prime of 0 is cosine of 0, which is just 1. And let me separate these a little bit so they're not all running together. So our second derivative of x is the derivative of cosine, which is negative sine. That means the second derivative at 0 is just negative sine of 0, which is still 0. And the third derivative, make that a little neater, of x is the derivative of negative sine, which is negative cosine. We know that the third derivative at 0 is equal to negative cosine of 0, which is negative 1. And we'll do one more just because we can. And we did the fourth derivative of x. You know, the derivative of cosine is negative sine, so negative sine times negative 1 is positive sine. Okay, so we know that the fourth derivative at 0 is just sine of 0, which is 0. Okay, so there's definitely a pattern there. Okay, so that means we know that sine of x written as a Maclaurin series is just f of 0, which is 0, plus f prime of 0, which is 1, times x, plus the second derivative at 0, which is 0, divided by, doesn't matter, it's still going to be 0, plus the third derivative at 0 is going to be negative 1, divided by 3 factorial, or you can just multiply it by 1 divided by 6, times x to the third power. Okay, and if we went one more, made that the fourth derivative at 0, divided by 4 factorial times x to the fourth power, and then it keeps on going after that. We see that would just end up being 0. Okay. But if we were looking for a pattern, we could just say that sine of x is equal to x minus, because this is just 0, that's 0, and that's 0, 1 over 3 factorial times x to the third power. And if we kept going, it would be plus, put the x to the fifth power, 1 over 5 factorial times x to the fifth power. Then it would be minus 1 over 7 factorial times x to the seventh power. Make that factorial a little bit neater. And then it would just keep going in that pattern. Move that up a little bit. And just a little bit of a side note. Let's say if you wanted to find sine of x squared for your Maclaurin series. Then you just get sine of x and replace it with x squared. That means if you had sine of x squared, then that would just be x squared minus 1 over 3 factorial times x squared to the third power plus 1 over 5 factorial times x squared to the fifth power minus 1 over 7 factorial times x squared to the seventh power, and it keeps on going. So that means your Maclaurin series for sine of x squared, there we go, would just be x squared minus 1 over 3 factorial, or you can put 1 over 6, doesn't matter, times x to the sixth power minus 1 over 5, well, plus 1 over 5 factorial, or 1 over 120 times x to the 10th power minus 1 over 7 factorial, and I'll just leave that as 7 factorial because I was too lazy to actually calculate that, times x to the 14th power. And it keeps on going after that. So this is just a little side note. In case you wanted to find sine of x squared, sine of x to the 3rd power, sine of x to the 5th power, they all kind of piggyback off of sine of x. All right, any questions on that one? All right. Okay, done writing. Okay, so we already saw that if we did sine of x, we ended up with x minus x to the 3rd power divided by 3 factorial plus x to the 5th power divided by 5 factorial minus x to the 7th power divided by 7 factorial plus x to the 9th power divided by 9 factorial, and it keeps on going in that pattern. Okay. Now, if we did the exact same thing for cosine, the pattern is actually really interesting. So cosine, you have 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 factorial minus x to the 6th power divided by 6 factorial plus x to the 8th power divided by 8 factorial, and it keeps on going. Oh, that should be minus. And that factorial looks a little bit odd, so let me rewrite it. There we go. And if we did the same thing for e to the power of x, we'd end up with 1 plus x squared over 2 factorial plus x to the 3rd power over 3 factorial plus x to the 4th power over 4 factorial, and so forth and so on. Okay, so what if we take that, just kind of separate that a little bit, and what if we replace x with negative I times x in your e to the power of x? Excuse me. Okay, well, that gives us e to the power of I times x, which is equal to 1 plus I times x, or negative I times x. Got my negative up there. Negative I times x plus negative I times x squared divided by 2 factorial plus negative I times x to the 3rd power divided by 3 factorial plus negative I times x to the 4th power divided by 4 factorial, and it keeps on going and going and going. So if you remember your complex numbers, then you remember that I squared is equal to -1. So we can take our e to the power of -I times x, and we can write that as 1 minus I times x. That I squared, well, negative times negative will be positive, so this will result in a positive, but that I squared is -1. That's negative, look, not negative I squared, negative x squared divided by 2 factorial, which is 2. Okay. So that I to the third power will give us I squared times I, which is -I. So that negative and that negative will end up being positive. But we know that we'll still have I to the third power, so that whole thing would have come off being negative anyway. So you have negative times negative times negative, which would end up being negative. So we have negative I times x to the third power over 3 factorial. And then we do the same thing here, but we know that if we have negatives multiplied 4 times to itself, it'll end up being positive. So we have I to the fourth power, which is just I squared times I squared. So that results in -1 times -1, which is +1. So this ends up being plus x to the fourth power over 4 factorial. And if we kept on going, we'd have plus I times x to the fifth power over 5 factorial, and so forth and so on and so on. And x to the sixth power over 6 factorial. And it'll keep on going. Okay, so what if we decide we're going to factor out an I? Oops, got my other. So that means we have to get all of the terms with an I next to each other. So e to the power of -I times x is equal to, so if we get all the terms without an I next to it, we have 1 minus x squared over 2 plus x to the fourth over 4 minus x to the sixth over 7 factorials. Got my factorials down there. There we go. Plus, now all the ones with an I, we're going to factor the I over here. Okay, so that one. Oh, wait a minute. Where did I just just checking on something. Because that would just be, it should be positive. Where did I made an error somewhere? Let me double check. If I can catch it. Okay, so that should be positive. I'll have to go back and double check that, but sorry about that. I'm trying to look and see where I made that negative, because that should be x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. I'll have to double check where I made an error there, because I know it's supposed to end up there. So I actually must have done something wrong there. So I'll go back and double check it. Thought I had it all figured out. But this gives us e to the power of negative I times x, which this one is just cosine of x. Plus I, and that one is just sine of x. Then I have to go back and double check, because that one little thing threw it off a little bit. So I have to find out why my calculation went off. And I've done this a million times, so I have no clue why. But this is Euler's formula. And of course, I thought I had it memorized, but that one little negative threw me off. I'll go back and double check that one. All right. Again, you might need this for some of the problems. You might not. It's just one of those interesting formulas. I see where I did it. Let me see. Nope, that didn't do it. I'll double check it later. It's going to bug me anyway, so I won't be able to sleep until I figure out where I did it. All right, anyone still writing? All right, let me set that aside. Okay, so let's say, for example, if we wanted to use the second Taylor polynomial, for f of x is equal to cosine of x at x is equal to 4 pi, to estimate cosine of 1 plus 4 pi. And we want to round to 4 decimal places if necessary. Okay, so we know that if we're looking for the second Taylor polynomial, that's just another way of saying p sub 2 of x. So we know that we are going to go to the second derivative term. So know that's f of c plus f prime of c times x minus c plus the second derivative at c divided by 2 factorial times x minus c squared. Okay, well, we know that f of x, that's our cosine of x. And our f prime of x is negative sine of x. And our second derivative at x is the derivative of negative sine, which is negative cosine of x. Oh, bless you. Now, at x is equal to 4 pi, we can find each one of those. So we know that f of 4 pi is just cosine of 4 pi, which is 1. And f prime of 4 pi is just negative sine of 4 pi. Which is 0. And the second derivative at 4 pi is just negative cosine of 4 pi. Which is negative 1. Okay, so we know that if we plug it into our p sub 2 of x, so p sub 2 of x is equal to f of c, which is just f of 4 pi, plus f prime of 4 pi times x minus 4 pi plus the second derivative at 4 pi divided by 2 factorial, which is just 2, but I'll write 2 factorial anyway, times x minus 4 pi squared. Okay, so if we plug in all of our values, we know that p sub 2 of x, our second Taylor polynomial, is equal to f of 4 pi, which is 1, plus f prime of 4 pi, which is 0, times x minus 4 pi. You don't have to write that since it's multiplied by 0, but I'll do it anyway, plus f prime of 4 pi, so that's negative 1, divided by 2 factorial, times x minus 4 pi squared. Okay. So if we simplify it, we know this term just disappears completely. That's p sub 2 of x is equal to 1. That negative 1, we can just bring that down and make that minus 1/2 x minus 4 pi squared. Okay, so if we wanted to estimate cosine of 1 plus 4 pi, we just replace x with 1 minus 4 pi. Let me write that note down before I start working on it. To estimate cosine of 1 plus 4 pi, replace x with 1 plus 4 pi. Same way we did with sine of x and x squared. If you know sine of x, then sine of x squared is just replacing x with x squared. Same thing here. Okay, so our p sub 2 of 1 plus 4 pi is just equal to 1 minus 1/2, bring that up a little bit, times 1 plus 4 pi minus 4 pi. Make that minus a little clearer. Minus 4 pi squared. Okay, so we have the plus 4 pi and minus 4 pi. They cancel each other out. So we have 1 minus 1/2 times 1 squared, which is just 1 minus 1/2, which is 1/2. If you want to estimate that to 4 decimal places, you just make 0.5 or 0.5000. Okay. So again, you don't need the 4 decimal places, but if Newton says write your answer in 4 decimal places, then you'd have to write it with the additional zeros. But only if they absolutely want it with 4 decimal places. All right. So any questions on that one? All right. Oh, anyone still writing? Okay. So let's say, for example, if we wanted to use the fourth Taylor polynomial, for f of x equals the square root of x at x is equal to 9, to estimate the square root of 10. And again, we're going to round to 4 decimal places if necessary. Okay, well, we know that the fourth Taylor polynomial P sub 4 of x is equal to f of c plus f prime of c times x minus c plus the second derivative at c divided by 2 factorial times x minus c. Probably should have started at the very end. Yep, I'll erase that and start at the very end, just because I know I'm going to run out of space. I am the worst person in the world when it comes to estimating how much space this will take. So f of c plus f prime of c times x minus c plus the second derivative at c divided by 2 factorial times x minus c squared plus the third derivative at c divided by 3 factorial times x minus c to the third power plus the fourth derivative at c divided by 4 factorial times x minus c to the fourth power. So I'm just going to go ahead and erase this one because I should have started at the far left from the beginning. Here we go. Okay, so once again, we know that our f of x is square root of x. And if we rewrite that as x to the 1/2 power, and using the power rule, we know that our f prime of x is 1 over 2 square root of x. Now our second derivative of x, we rewrite that as 1/2 times x to the negative 1/2 power, then that will equal negative 1/4 times the square root of x to the third power. And our third derivative of x, we factor out that 1/2 and rewrite that as x to the negative 3/2 power. That would give us 3/8 times the square root of x to the 5th power, or x to the 5/2 power. And the fourth derivative, that's going to be negative 15 over 16 times the square root of x to the 7th power. Okay, now at x is equal to 9, we know that f of 9 is just the square root of 9. I'll rewrite that over here. F of 9 is equal to the square root of 9, which is 3. And f prime of 9 is just 1 over 2 times the square root of 9. which is just 1 over 2, times the square root of 9, which is 3. That's just 1 over 6. So our second derivative at 9 is equal to -1 divided by 4 times the square root of 9 to the third power. Well, we know the square root of 9 is 3, so 3 to the third power times 4 will give us -1 over 108. Divided by the third derivative at 9 is 3 divided by 8 times the square root of x to the fifth power. Nope, 9 to the fifth power. So that gives us 3 to the fifth power times 8. So this ends up being 3 divided by 1,944, which can be simplified because both are divisible by 3. So we end up with 1 over 648. And our fourth derivative at 9 we can rewrite that as -15 divided by 16 times the square root of 9 to the seventh power. So that will end up giving us 3 to the seventh power times 16 in our denominator. So that's -15 divided by 34,992. Okay, but that can be simplified because both of those are divisible by 3. So we end up with a simplified -5 divided by 11,664. And I'll just kind of separate this a little bit. Okay, so we know that our fourth Taylor polynomial is going to equal f of 9 plus f prime of 9 times x minus 9 plus the second derivative at 9 divided by 2 factorial times x minus 9 squared plus the third derivative at 9 divided by 3 factorial times x minus 9 to the third power plus the fourth derivative at 9 divided by 4 factorial times x minus 9 to the fourth power. Okay, so that's going to equal your f of 9. That's just 3. Plus your f prime of 9, that's 1/6 times x minus 9. plus your second derivative at 9 is negative 108, well, 1 over 108, divided by 2 factorial, so you can just multiply that by 1 over 2 factorial, times x minus 9 squared. Plus the third derivative at 9 is 1 over 648 divided by 3 factorial, so we can just multiply it by 1 over 3 factorial times x minus 9 to the third power plus the fourth derivative at 9, which is negative 5 divided by 11,664 times x minus 9 to the fourth power. So if we simplify this just by multiplying our terms together, then that would give us p sub 4 of x is equal to 3 plus 1 over 6 times x minus 9 minus 1 over 216 times x minus 9 squared plus 1 over 3,888 times x minus 9 to the third power minus 5 divided by, oh, forgot my 4 factorial. So busy worrying about 4 factorial. So it should be divided by 4 factorial. I was concentrating on squeezing all of that into one spot. So if we get 11,664 times 4 factorial, we'll get 279,936 times x minus 9 to the fourth power. Okay, so we want to use that to estimate the square root of 10. Remember to estimate the square root of 10, just replace x with 10. Because remember, your f of x is already square root of x. So you're not going to replace x with square root of x, because that would be the square root of a square root of x. So you're just going to replace x with 10. Okay, so we know that p sub 4, our fourth Taylor polynomial, at 9, at 10, is equal to 3 plus 1 over 6 times 10 minus 9 minus 1 over 216 times 10 minus 9 squared plus 1 divided by 3,888 times 10 minus 9 to the third power. And make that 3 a little neater than that. Minus 5 divided by 279,936 times 10 minus 9 to the fourth power. So we can see all of those 10 minus 9s just end up being 1. So So we have 1, 1 squared, 1 to the third, 1 to the fourth power. So we can just rewrite this as 3 plus 1 over 6 times 1, which is the same thing, minus 1 over 216 times 1 squared, which is the same thing, plus 1 divided by 3,888 times 1 to the third power, minus 5 divided by 279,936 times 1 to the fourth power. So that just stays. So if you do that and you want the exact answer, then that ends up being 885,235 divided by 279,936. And if you plug that into your calculator, you'd get approximately 3.16228. Rounded to, oh, that's running out of room. All right, one little section here for our rounded answer, which is 3.1623. So that is our estimated square root of 10 using the fourth Taylor polynomial. So lit up a little bit. So it's a little bit lengthy. Excuse me. All right. So let's say, for example, if you wanted to find the first 4, and clean up that O a little, non-zero terms of the Maclaurin series, for f of x is equal to cosine of 3x divided by 2, and write as a sum. Okay, so if you remember, we know that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth power over 8 factorial, and it keeps on going in that pattern. Okay, so we could actually get our cosine of x and write it as an alternating series. That's just equal to the sum from n equals 0 to infinity of -1 to the nth power times x to the power of 2 times n divided by 2 times n factorial. So that's just the series version of our cosine of x. Okay, so now we just have to replace, and make that L a little neater, x with 3x divided by 2. Okay. Now, if you wanted to, you could have plugged it into this one, but decided to plug it into our actual series. So we know that cosine of 3x divided by 2 is equal to the sum from n equals 0 to infinity of -1 to the power of n of 3x divided by 2 to the power of 2n. And all of that divided by 2n factorial. Okay, so we know that if we take our 3x divided by 2 to the power of 2n, so 3x divided by 2 to the power of 2n, we divide that by 2n factorial, we know that we can rewrite that as 3x to the power of 2n divided by 2 to the power of 2n, and all of that divided by 2n factorial, we could just rewrite that as times 1 over 2n factorial. So that means that our cosine of 3x divided by 2, we can rewrite that as the sum from n equals 0 to infinity of -1 to the power of n times 3x to the power of 2n divided by 2 to the power of 2n times 2n factorial. Okay, so now all we have to do is just plug in 0, 1, 2, and 3, our first 4 terms. So we plug in our n is equal to 0. We get -1 to the power of 0, which is 1, times 3x to the power of 2 times 0, which is 0, so that's 1. So really you just get 1 times 1 divided by 1 times 1, because 0 factorial is 1. So when n is equal to 0, that first term is just 1. Okay, now we have to do our n is equal to 1. So -1 to the first power is -1. So this is going to be a minus. So we have 3x to the power of 2 times -1. So that's 3x times 2 to the power, well, 2 to the power of -1 is just -2. So that gives us 1 over 9x squared. Nope, actually that's still, yep, it would be 1 over 9x squared because n is equal to 1 here would give us 2 squared. Yep, so the x squared will be up here. Because we have negative 1 over 9 x squared, because we have 2 times 2 to the power of 2, so that's 4, times 2 factorial, which is 2. So we have 16, so that gives us, 9 over 8 x squared. There we go. I was thinking of n is equal to 2. Plus, now when n is equal to 2, we have negative 1 squared, so we know that stays positive. So we have times 3 to the 4th power, which is 81, times x to the 4th power, which we'll just leave as x to the 4th power, divided by 2 to the power of 4, which we can leave that as 16 times 2 times 2, which is 4, so times 4 factorial. That will end up giving us 16 times 4 times 3 times 2 times 1 is 24. Plus, when our n is equal to 3, we have negative 1 to the 3rd power, so this will end up being minus negative 1 times negative 1 times negative 1. So we have 2 to the 2 times 3, which is 6. So we have 3 to the 6th power. So that gives us 729 times x to the 6th power divided by 2 times 2 to the 2 times 3 power, which is 2 to the 6th power, which is 64, times 2 times 3 factorial, which is 6 factorial. Ooh, nose itch. Okay, so if we simplify each term, at least the ones that need to be simplified, we have 1 minus 9 over 8 x squared plus 81 divided by 384 times x to the 4th power minus 729 divided by 64 times 6 factorial. We can just go ahead and simplify that. It ends up simplifying to 81 divided by 5,120 times x to the 6th power. The third term can be simplified too if you wanted to. Like I said, I'm pretty sure Newton should take that as your answer, but if you wanted to, you could simplify it again. Because 81 and 384 are both divisible by 3. So we have plus 27 over 128 x to the 4th power minus 81 over 5,120 times x to the 6th power. So again, I don't think Newton will be that picky. They could be. I don't put anything past that program. Any questions on that one? All right. Okay, so what if we wanted to find the first four non-zero terms for f of x is equal to the natural log of 1 minus x? Okay, so we know that the natural log of 1 plus x, there's actually a series for that, and that's the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times x to the power of n divided by n. So with that natural log of 1 minus x, we want to put it in this form. So that means we can take that natural log of 1 minus x, and we can rewrite that as the natural log of 1 plus negative x. So that just means all we have to do is replace every x with negative x. Place x with negative x in our formula, or our series formula. So we know that's going to equal the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times negative x to the power of n divided by n. Okay, so that will give us the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times that negative x to the power of n. Remember, we can rewrite this as negative 1 times x. So if we distribute that n to each of those factors, we'll have negative 1 to the power of n times x to the power of n divided by n. Okay, so if we combine these two, so if we have negative 1 to the power of n plus 1 times negative 1 to the power of n, since they have the same base, all we have to do is add the exponents. That's negative 1 to the power of n plus 1 plus n. So we have negative 1 to the power of 2n plus 1. So we can rewrite that as the sum from n equals 1 to infinity of negative 1 to the power of 2n plus 1 times x to the power of n divided by n. So now all we have to do is plug in values from 1 to 4. So when n is equal to 1, we have negative 1 to the power of 2 times 1, which is 2, plus 1 is 3. So negative 1 to an odd exponent is going to come out to be negative. Move that equal sign down a little bit. Okay, so we have x to the first power divided by 1 is just x. Okay, now we have to go, n is equal to 2. So negative 1 to the power of 2 times 2 plus 1 is to the fifth power, so we know that's going to be negative of x squared divided by 2. N is equal to 3. Well, we know 2n plus 1 is going to be odd each and every time anyway, so each term is going to be odd. That gives us 6 plus 1, which is 7, so it's negative x to the third power over 3. And when n is equal to 4, let's minus x to the fourth power over 4. All right, so are there any questions on that one? All right. Okay, so let's say, for example, if we wanted to find the first 4 terms of non-zero terms, let's be a little specific. For the Maclaurin series, f of x is equal to the hyperbolic sine of 2x. Now, I'm not sure if Newton will give you hyperbolic functions or not, but just in case, this way you'll see how to approach it. Okay, now with this one, you just want to remember that the hyperbolic sine, bless you, of x is equal to e to the power of x minus e to the power of negative x divided by 2. Okay. So we already know that e to the power of x is equal to 1 plus x plus x squared over 2 factorial plus x to the third power over 3 factorial plus x to the fourth power over 4 factorial, and so forth and so on. Okay, but we can rewrite that as a series. So e to the power of x can just equal the sum from n equals 0 to infinity of x to the power of n divided by n factorial. So that gives us e to the power of x. So the hyperbolic sign of 2x would be e to the power of 2x minus e to the power of negative 2x divided by 2. E to the power of 2x minus e to the power of negative 2x divided by 2. That means our e to the power of 2x, we can rewrite that as 1 plus, we're going to replace every x with 2x. So that becomes 1 plus 2x plus 2x squared is going to be 4x squared divided by 2 factorial plus 2x to the third power. 2 to the third power is 8, so 8x to the third power divided by 3 factorial. And 2x to the fourth power is 16x to the fourth power divided by 4 factorial. And it keeps on going. But we're going to stop at those terms. And we know that e to the power of negative 2x, well, the first term is also 1. Minus minus 2x, since we're replacing x with negative 2x. Okay, so negative 2x squared is still going to be positive. So that's plus 4x squared. Oops, I got to put my squared up there. Divided by 2 factorial. Okay, and negative 2x to the third power is going to be negative, because negative 2 times negative 2 times negative 2 is negative 8. X to the third power divided by 3 factorial. And negative 2x to the fourth power is going to be positive 16x to the fourth power divided by 4 factorial. And it keeps on going. So if we want to find e to the power of 2x minus e to the power of negative 2x, then we just have to get these two and subtract them. And you can do it vertically if you want to, or you can expand them horizontally, completely up to you. So e to the power of 2x is 1 plus 2x plus 4x squared over 2 factorial plus 8x to the third power over 3 factorial plus 16x to the fourth power over 4 factorial, and it keeps on going, minus e to the power of negative 2x, which is 1, minus 2x, plus 4x squared over 2 factorial, minus 8x to the third power over 3 factorial, plus 16x to the fourth power over 4 factorial, and it keeps on going. Okay. So now we just have to distribute that negative and combine like terms. So we have 1 minus 1, which is 0, so those two just cancel each other out. So we have 2x plus 2x, which is 4x. 4x squared divided by 2 factorial minus 4x squared divided by 2 factorial. So those two cancel each other out. We have 8x to the third power divided by 3 factorial plus 8x to the third power divided by 3 factorial. So we have plus 16x to the third power divided by 3 factorial. We have 16x to the fourth power minus 16x to the fourth power. So that disappears. Okay. And the next two terms, since we ended up shutting it off because we ran out of room, it's 64x to the fifth power first. Then we have the 256. So 64x to the fifth power divided by 5 factorial plus 256x to the seventh power divided by 7 factorial. Okay, but we did not have enough room to write all of those, so I had to kind of leave it there. But if we kept on going, these would have been the next couple of terms. So this is just our e to the power of 2x minus e to the power of negative 2x. Okay, but we know that our hyperbolic sine of 2x is e to the power of 2x minus e to the power of negative 2x divided by 2. So we're going to divide this by 2, and we can go ahead and divide all of that by 2 in one swoop. Okay, so 4x divided by 2 gives us 2x. And 16x to the third power divided by 3 factorial. If we divide that by 2, then 16 divided by 2 is 8. So that's plus 8x to the third power divided by 3 factorial. Plus 64 divided by 2 is 32. So that's 32x to the fifth power divided by 5 factorial. Plus 256 divided by 2 is 128. So we have 128x to the seventh power divided by 7 factorial. Okay. So if we expanded all of our factorials and simplified each fraction, we'd end up with 2x plus 4x to the third power divided by 3, because the 2 simplified there, plus 4x to the fifth power divided by 15, plus 8x to the seventh power divided by 315. So that's just the simplified version of it. Oops. All right, any questions on that one? I know it's a little on the lengthy side, so I try to condense it as much as possible without leaving anything out. All right, any questions? All right. Straighten these up. Okay, so now we're going to go ahead and start on section 10.4. And move that over a little. Which covers a binomial series. Excuse me. Okay. So let's say if we wanted to find the Maclaurin series, for f of x is equal to 1 plus x to the power of some constant k. Okay, well, we know that our f of x is equal to 1 plus x to the power of k. So f of 0 would just be equal to 1. So f prime of x, we use the chain rule. We bring down the k times 1 plus x to the power of k minus 1 times the derivative of what's inside is just 1, so we can leave it there. So we know f prime of 0 is equal to k times 1 plus 0 to the power of k minus 1, which is just k. So if we wanted to find the second derivative, we have our constant k. We bring down the k minus 1 times 1 plus x to the power of k minus 1 minus 1, just k minus 2. So the second derivative at 0 is just equal to k times k minus 1 times 1 plus 0, which is 1, to the power of k minus 2. It's just k times k minus 1. we wanted to do the third derivative, the third derivative of this function is k times k minus 1, those constants that are already there. So this derivative, we bring down the k minus 2 times 1 plus x to the power of k minus 2 minus 1, which is k minus 3. So our third derivative at 0 is just k times k minus 1 times k minus 2 times 1 plus 0, which is 1, to any power is just going to be 1. So you can kind of see the pattern. It keeps on going in that pattern. Okay. So if we went on in that pattern, we know that the nth derivative of x would just be k times k minus 1 times k minus 2 times k minus 3, and it keeps on going in that pattern. So you have k minus n plus 1, and then eventually 1 plus x to the power of k minus n. So these are just all of your coefficients that you can kind of see just kept building and building and building. And we know that for the Maclaurin series, we're going to need the nth derivative at 0. Well, we know that's just going to equal k times k minus 1 times k minus 2 times k minus 3, all the way until your k minus n plus 1. Okay, so we know that the Maclaurin series for this particular function is the sum from n equals 0 to infinity. Oh, bring that up a little bit. Here we go. Of the nth derivative of 0 divided by n factorial times x to the power of n. Which we know is just equal to, if we expand it, 1 plus k times x. That's our first derivative. Plus k times k minus 1 divided by 2 factorial times x squared, plus k times k minus 1 times k minus 2 divided by 3 factorial times x to the third power, and it keeps on going in that pattern. Okay, until eventually we hit the nth derivative, which is k times k minus 1 times k minus 2, all the way until k minus n plus 1. Give myself a little more room just to make sure. K times k minus 1, k minus 2, all the way to k minus n plus 1, divided by n factorial. And we multiply that by x to the power of n. So this leads us up to the definition of our binomial series. All right, anyone still writing? All right. Okay, so the definition states that if you have some real number k, so if it's a real number, and we know that the absolute value of x is less than 1, then we know that 1 plus x to the power of k is equal to the sum from n equals 0 to infinity kn times x to the power of n. And that's just the coefficient notation. I'll kind of go through that a little bit more. Where we know that this is the coefficient, is the, I guess you can call it the traditional notation for the coefficient of the binomial series. And that binomial series is 1 plus x to the power of k is equal to 1 plus k times x plus k times k minus 1 divided by 2 factorial times x squared plus k times k minus 1 times k minus 2 divided by 3 factorial times x to the third power, and it kind of keeps on going. Okay. And we can write this as in its series version, the non-expanded version of it. You can rewrite it as the sum from n equals 0 to infinity of your coefficient notation times x to the power of n. So this is kind of the condensed version of this. All right, anyone still writing? Okay. So let's say, for example, if we wanted to find the first four terms of the binomial series for the function f of x is equal to 1 divided by 1 plus 5 over x. Okay. So if you remember, we have f of x and it equals 1 plus x to the power of k, we know we can rewrite that as the sum from n equals 0 to infinity of our coefficient times x to the power of n. Where if we expand that, we know that also equals, give them a little more room, 1 plus k times x plus k times k minus 1 divided by 2 factorial times x squared plus k times k minus 1 times k minus 2 divided by 3 factorial times x to the third power, and it keeps on going. So it's just a little bit of a side note. Okay. So in order to use the binomial series, we have to rewrite our f of x to where it's in this form of f of x. So what we have to do is we have to rewrite it. So we're going to rewrite it as f of x is equal to 1 plus 5 over x to the negative 1 power. Okay, so we can see right here. I'll make that a little bit bigger so I have more room to write. So we see it's in the f of x is equal to 1 plus x to the power of k form, just by making that one little change. Okay, so we see right here, our k is equal to negative 1. And we see here, where the x is in our formula, it's a 5 divided by x. So we're now going to replace our x with 5 divided by x, and we're going to replace the k with negative 1. So if we saw this in the more traditional form, then we could just say that our f of x is equal to the sum from n equals 0 to infinity. Since k is equal to -1, we're just going to put it at -1 and n, and that x, we're going to make it 5 over x to the power of n. So all we did was take our traditional form, place k with -1 and x with 5 over x. Which means we're going to do the exact same thing in our expanded form. Replace k with -1 and x with 5 over x. So we know that this is just equal to 1 plus k times x is going to be -1 times 5 over x. So we're going to do that for every single k and x. Okay. Plus, you have -1 times k minus 1 just becomes -1 minus 1 divided by 2 factorial. And that x squared becomes 5 over x squared. Plus that k becomes -1 times k minus 1 becomes -1 minus 1 times that k minus 2 becomes -1 minus 2 divided by 3 factorial, and that x to the third power becomes 5 over x to the third power. Okay. So here we have -1 times -2. -1 times -2, which is +2. And here, in this numerator, you see we have -1 times -2 times -3. Okay, so that gives us -6. So if we rewrite each term, we have 1 minus 5 over x plus 2 divided by 2 factorial times 5 over x squared is just 5 squared over x squared. Okay, so since all of these multiplied gives us -6, let me make that negative a little clearer. There we go. That becomes -6 over 3 factorial. And 5 over x to the third power is just 5 to the third power over x to the third power. Okay, so now we just simplify it one last time. So that's 1 minus 5 over x. 2 factorial is equal to 2, so these two just cancel each other out and become 1. So that leaves us with plus 5 squared, which is 25, over x squared, minus 6 and 3 factorial, well, 3 factorial is 3 times 2 times 1, which is 6. So those two cancel each other out. So we have 5 to the third power, which is 125, divided by x to the third power. And those are the first 4 terms of the binomial series. Okay. So are there any questions on that one? So after a few times, you kind of see a pattern to it. So it takes a little bit of practice. Right. Let's say if we wanted to, but if we wanted to find the first 4 non-zero terms of the binomial series for the function f of x is equal to 1 divided by the 4th root of 1 minus 2x to the 4th power. Okay, so remember that your f of x is equal to 1 plus x to the power of k, which in series form, or traditional series form, that's the sum from n equals 0 to infinity of our coefficient times x to the power of n. Make that k a little bit clearer. So if we expand it, that just means we have 1 plus k times x plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 over 3 factorial times x to the third power, and et cetera, and so on. So let me write that third power a little clearer. There we go. Okay, so let's look at our f of x. Okay, so we have f of x is equal to 1 divided by the fourth root of 1 minus 2x to the fourth power. Okay, well, we can rewrite that as 1 divided by, instead of the fourth root, we can make that 1 minus 2x to the fourth power raised to the 1/4 power. And we can rewrite that again as 1 minus 2x to the fourth power raised to the negative 1/4 power. Okay, but remember, we want it in this form. So we can't have that minus, so we have to rewrite it one more time. So it's 1 plus negative 2x to the fourth power to the negative 1/4 power. Okay. Now this matches this form. So we can see right here that our k is equal to negative 1/4. And where the x is here, we have negative 2x to the fourth here. So that means we just have to replace x with negative 2x to the fourth. Okay, so that means that our f of x, which we rewrote it in the form of 1 plus negative 2x to the fourth power raised to the negative 1/4 power, if we put it in the traditional form, that would just be the sum from n equals 0 to infinity of n, and that k will be replaced with negative 1/4. And instead of x to the power of n, we'll have negative 2x to the fourth power to the power of n. Okay, now if we plug in those values for k and x into our expanded form, we will end up with, we have 1 plus k times x, so that's negative 1/4 times negative 2x to the fourth power, plus k times k minus 1, so we have 1/4, negative 1/4. Get rid of that. There we go. So negative 1/4 times negative 1/4 minus 1, divided by 2 factorial. Instead of times x squared, it's going to be negative 2x to the 4th power squared. Plus, we have k, which is negative 1/4, times k minus 1, so negative 1/4 minus 1, times k minus 2, so negative 1/4 minus 2, divided by 3 factorial. And instead of x to the 3rd power, we're going to have negative 2x to the 4th power to the 3rd power. Okay, so if we simplify each term, we have 1. And if we go ahead and multiply these two, we end up with positive 2/4, which is just positive 1/2, times x to the 4th power, plus we have 1/4 times 1/4 minus 4/4 is negative 5/4. So we have, and I'll just kind of write that above this. So negative 1/4 times negative 5/4. I wanted to give that a little more room. So this part of it would just become negative 1/4 times negative 5/4. Okay, so negative 1/4 times negative 5/4 divided by 2 factorial, or you can just put 2, times negative 2 to the 2nd power is positive 4. And x to the 4th power squared will give us x to the 8th power. Okay. Plus, now these 3 factors, they will give us negative 1/4 times negative 1/4 minus 1. Well, we already know negative 1/4 minus 4/4 is negative 5/4. And negative 1/4 minus 2, so we have negative 1/4 minus 8/4 would give us negative 9/4. Okay, so we have negative 1/4 times negative 5/4 times negative 9/4 divided by 3 factorial times negative 2 to the 3rd power is negative 8. And x to the 4th power raised to the 3rd power is x to the 12th power. So if we simplify each term a little bit more, we have 1 plus 1/2 x to the 4th power. And this 4 can actually cancel out with that 4. So we wrote this as negative 1/4 times negative 5 over 4 times 1/2, then this 4 could cancel out with either one of those 4s. So that leaves us with negative 1 over 4 times 1/2. Well, the negative times negative is positive, so that becomes positive. So we have positive 5 over 8 times x to the 8th power. Okay. So with this one, we have 9 times 5 times 8. And we have negative times negative and a negative times negative. So we have an even number of negative factors, so it becomes positive. So if you have 9 times 5 is 45. 45 times 8 is 360. Divided by 4 times 4 times 4 times 3 factorial is 384 times x to the 12th power. Okay. So we can simplify. We could have simplified it first and then multiplied it, but it doesn't really matter as long as it's simplified. Okay, so we know that 360, that's 15 times 24. And we know that 384 is 16 times 24, where the two 24s cancel each other out. So that gives us 1 plus 1/2 x to the 4th power plus 5 over 8 times x to the 8th power plus 15 over 16 x to the 12th power. Okay. So the first step isn't too bad. You just want to put it into that 1 plus x to the power of k form. And even the next step, I don't think it's too bad. You're just replacing k and x with the appropriate values and functions. Now, once you replace it, it might get a little messy. But I think the first two steps really aren't too bad. It's just very detailed parts of algebra you're doing after that point. Okay. But any questions on this one? All right, so we'll finish up with 10-4 on Monday. Gotta make sure I remember which day it is. Okay. I don't know why I was thinking yesterday, I was thinking it was Thursday, and today I'm thinking today is Wednesday. All mixed up. All right, but everyone have a good weekend, and I will see you on Monday.
Have a nice day.
All right, you too.
Have a good weekend.
You do the same.
Have a good weekend.
You too. Uh-oh, see, we have a question. All right, thank you, Mohammed. You have a good weekend too. Excuse me.